The topic of this lecture will be the stability and structure of cycloalkanes. The most common cycloalkanes that we see are cyclopentanes and cyclohexanes, and this has to do with their stability. So what we're going to do now is go through the simplest cycloalkanes up to a six-membered ring and see if we can determine why, due to their stability, cyclopentane and cyclohexane are most common. The smallest cycloalkane we can have is cyclopropane with 3 atoms, because 3 atoms are required to make the cyclic structure. Cyclopropane contains 3 sp3 hybridized carbon atoms in a ring, and remember that each of these carbon atoms then will have 2 hydrogens on them. So we have 3 sp3 hybridized carbons, they have 4 sigma bonds each. The bond angle should be for sp3 hybridized carbons 109.5. But because of the constraint that the ring structure puts on these carbon atoms and their bonds to one another, the bond angles within the cyclopropane molecule are actually 60 degrees. This puts a lot of strain on this structure that is specifically called angle strain, which results from the carbon-carbon bond angles being constrained to much smaller than what they would prefer to be according to Vesper theory, 109.5. Angle strain isn't the only type of strain present in the cyclopropane molecule. We can see the other type of strain if we draw a Newman projection down one of the carbon-carbon bonds. It doesn't matter which carbon-carbon bond you choose to look down, they're all equivalent, and so we're going to choose to put one of the carbons in the ring in the front and one in the back. And it may help you now to actually make this structure with your modeling kit so that you can see why I'm drawing the Newman projection the way I'm drawing it. There really is no other way due to the constraints that the 3-membered ring puts on these sp3 hybridized carbons. And so what this is going to look like is all of the bonds are going to be eclipsed because there's no way to rotate that single bond between the carbons in a way to get the hydrogens to be staggered, because there just isn't any flexibility in a 3-membered ring. And so what this Newman projection is going to look like, on our front carbon we have 2 hydrogens and then the carbon-carbon bond to the 3rd carbon in the ring. That is a CH2 group. And on the back carbon we also have 2 hydrogens and the bond to the same carbon of the 3-membered ring. And all of these bonds are eclipsed. This results in torsional strain, as we discussed earlier this week. So cyclopropane suffers both from angle strain and torsional strain, and the combination of angle strain plus torsional strain gives us something called ring strain. And cyclopropane has the highest ring strain of any cycloalkane. Next, we'll look at cyclobutane. Cyclobutane is a 4-membered ring. It contains 4 sp3 hybridized carbons. And so again, the desired bond angles are going to be 109.5. But due to the constraint that the 4-membered ring puts on those sp3 hybridized carbons, the actual bond angle is 90 degrees. So again, we have angle strain, although it's not quite as bad as in the cyclopropane example. So next we're going to look at a Newman projection. And again, I would suggest making the model of cyclobutane so that you can see what I'm drawing in my Newman projection. Again, it doesn't matter which carbon-carbon bonds we look down, but whichever carbon-carbon bond we choose, we actually have 2 carbon-carbon bonds parallel to one another. So we're actually looking down both of those carbon-carbon bonds at the same time. And so our Newman projection will look like this. So in our Newman projection, we see all 4 atoms of the cyclobutane in Newman projections, 2 on the left and 2 on the right. And in the front we see the carbon-carbon bond between the 2 front carbons, and in the back we see the carbon-carbon bond between the 2 back carbons, and they are eclipsed. And we also see 2 hydrogens on each front carbon and 2 hydrogens on each back carbon. Again, these are mostly eclipsed, although there is a little bit more flexibility in a 4-membered ring than there is in the 3-membered ring. For the most part, we still have all of our bonds almost entirely eclipsed. And remember that eclipsed bonds give us torsional strain. So cyclobutane has angle strain and torsional strain, which means that it has ring strain, although the ring strain isn't quite as bad as it is in the cyclopropane ring. Next, we'll look at a 5-membered ring, cyclopentane. Cyclopentane has 5 sp3 hybridized carbons. Its bond angle should be 109.5. And its actual bond angles, because of the flexibility with having 5 carbons, end up being about 108 degrees. So we're very close to having the 109.5 degree angles predicted by VSEPR. What this means is that we have very little angle strain. This is one of the reasons that cyclopentanes are one of the more common cycloalkanes, because they have low angle strain. Having more bonds leads to more flexibility, which also helps with torsional strain. Let's look at that Newman projection. And again, if you haven't already, I would suggest pausing the video and making a model of cyclopentane before we draw these Newman projections. So when we look down one of the carbon-carbon bonds of cyclopentane, what we see is that all of the other bonds are out of this plane, and so we only see a single carbon-carbon bond in a Newman projection of cyclopentane at one time. And so my front carbon has 2 hydrogens and then a carbon of the rest of the cyclic structure. And my back carbon has 2 hydrogens and a carbon from the cyclic structure. And so right now in my Newman projection, I have the front carbon, the back carbon, and 2 other carbons. That's 4 carbons. We have 1 more carbon, and that connects the 5-membered ring. And so what we can see, and hopefully you can also see this in your model, that when we have 5 bonds, we have quite a bit of flexibility, and we're able to get almost all of these groups completely staggered around our Newman projection. And what that means is then that we have no torsional strain, and since we have very little angle strain, we have very little ring strain. So since cyclopentane has low ring strain, it's low in energy, it's very stable, and that is why it is one of the cycloalkanes that we see most commonly in organic chemistry. The last cycloalkane we're going to look at is cyclohexane. Cyclohexane has 6 sp3 hybridized carbons. Again, our bond angles should be, according to VSEPR, 109.5. If this structure were planar and looked how I've drawn it on the page here, we would expect the angles to be 120 just looking at it. But because cyclohexane has 6 bonds, it's much more flexible, and its actual bond angles measure 109.5, exactly what they should be. This means that we have no angle strain. In order to attain these 109.5 degree angles, a cyclohexane ring adopts something called a chair conformation. That chair conformation looks like this. It's called a chair because it has a head and a footrest, kind of like a lounge chair. I would strongly suggest that you make a model of cyclohexane and see if you can form it into a chair conformation such as this, so that you can see what we mean, what we're trying to represent with our flat drawing of a 3-dimensional chair, and it will also help with the Newman projection that we're going to draw next. When we're looking at a Newman projection of a chair conformation of a cyclohexane, we can see that there are 2 bonds that will be in the Newman projections at the same time. So for example, if we're looking down this bond is parallel to that bond, and so we'll be looking down both of them next to one another in the same Newman projection. And that Newman projection will look like this. The front carbons will each have 2 hydrogens, and the 3rd spot on each of those carbons will be to the same atom, which is this atom here, which connects the front 2 carbons. The back carbons will also each have 2 hydrogens, and the 3rd spot on each of these back carbons will be a connecting carbon as well, this carbon, which will look something like this. And so this is what a Newman projection of a chair conformation of cyclohexane looks like. And again, hold your model looking down 2 parallel bonds so you can see what we're trying to represent with this flat Newman projection in that 3-dimensional chair cyclohexane. So what you'll see from this Newman projection is that all of the bonds in cyclohexane are staggered, and that means there is no torsional strain. And so cyclohexane has no angle strain and no torsional strain, which means that it has no ring strain. Cyclohexane is the most stable of the cycloalkanes, and that's why we see it so commonly in organic chemistry. We're going to spend the most time on cyclohexane because it's the most stable and the most common, and so next I'd like to show you how to draw a proper chair conformation of cyclohexane. The chair conformation is 3 sets of parallel lines that form a ring. One set of parallel lines are here and here. Another set of parallel lines are here and here. And the final set of parallel lines are here and here. And so I'd recommend pausing the video for a moment and practicing drawing your cyclohexane. And again, you might want to have your model handy so that you can start to understand what we mean and how we're representing this three-dimensional object on the two-dimensional page. Once we've drawn the chair conformation, there are very specific locations of each of the substituents on each of the carbons of the ring. Each carbon has two types of substituents. One that points up and down along the axis of the cyclohexane ring. These substituents are called axial because they're parallel to the axis going straight through the middle of the cyclohexane ring. The other type of substituent, which is found on every single one of these carbon atoms, are called equatorial. They're called equatorial because they stick out along the equator of the cyclohexane molecule. You'll notice that every one of these equatorial substituents is parallel to one of the sets of lines that make up the cyclohexane ring. For example, this substituent is parallel to this and this bond, as well as this bond. And these substituents are parallel to this bond and this bond. And this substituent and this substituent are parallel to this bond and this bond. And so hopefully that will help you arrange your equatorial substituents around the cyclohexane ring. What I'd like you to do with your modeling kit now is pause this video and find each of the 6 axial and each of the 6 equatorial substituents on your model of a cyclohexane chair conformation. And so what cyclohexane in a chair conformation looks like with all the substituents is this. And we can label each of these axial or equatorial and notice that there is an axial and an equatorial substituent in every single one of the carbons. So again, I would recommend practicing drawing your cyclohexanes with each of these substituents drawn in. It's very important that you get comfortable drawing axial and equatorial substituents properly on each of these positions because we're going to do a lot with cyclohexane in the future. And it's important to know whether a substituent is axial and equatorial, and it's important to be able to portray that to other people, including me, for example, on an exam. So I'd practice this a little bit and bring any questions you have to class.